So the 30, 60, 90 right triangle is unfortunately not as quick to develop as the 45, 45, 90 because it's not an isosceles triangle. So we can't just immediately pop out with, hey, let's call these two sides this length and just go from there. We need to be a little bit more creative with this one. Oddly enough, what we're going to start with is not even a right triangle. We're going to start with an equilateral triangle. An equilateral triangle which has all three sides and all three angles. Excuse me, let me make this a little bit bigger so we can see what we're dealing with better. It has all three sides and all three angles the same. So each angle is 60 degrees. This angle up here is 60 degrees. This one down here is also 60 degrees. The side lengths are all the same as well. Now, bear with me for a moment. I get to choose however big I want this to be, because remember, whether this is a big or small, medium or small triangle, the trigonometric functions are going to evaluate the same no matter what. So I'm going to choose a very particular side length here that's going to suit our purpose as well. I'm actually going to choose the side length to be 2, which might seem odd at first. If you think about the 45, 45, 90, I chose 1. So why would I choose 2 here? Well, because this isn't the triangle we need. We need to construct the 30, 60, 90 right triangle. And equilateral triangles are really, really nice because there are many things you can do with a triangle. You can bisect the angles, you can bisect the sides, you can find the altitude, that is a line that is perpendicular to the base that goes up to the highest point of the triangle. And on an equilateral triangle, these are all the same thing. The perpendicular bisector of any side is also the angle bisector of the angle across from it. That is to say, if I were to take the very top vertex of the triangle right there and drop a line straight down perpendicular to the base, it would cut this angle in half, meaning 30 degrees on each side. So let's now take out that 60 that we have there and realize that this half over here is now only 30 degrees. And because this is perpendicular to the base, this is a 90 degree angle. So what we've done is created a 30 degree, 60 degree, 90 degree right triangle by using half of the equilateral triangle, which is exactly why I chose a side length of 2, because not only does this bisect the angle, it also bisects the base. So I chose 2 because I can easily split it into 1 and 1. Of course, this side of it doesn't really matter. We're going to get rid of this entire side of the triangle. And what we have here is a 30, 60, 90 right triangle, where we know the lengths of 2 of the sides. The Pythagorean theorem will produce the length of the third side. Now be careful here. We have 1 for one of the legs of the triangle, but we do not have the other. What we do have is the hypotenuse. So what we have is 1 squared is 1. 1 plus b squared is equal to 2 squared, which is 4. We subtract the 1 from both sides. We have b squared is equal to 3. And therefore b is equal to the square root of 3. That is the length of the third side. So 1 square root of 3, and 2. Well, again, like the 45, 45, 90, we have one side that has a not so friendly value, but, well, we can work with that. Now, we do have two different angles in here that showed up in our discussion of angles in the previous lesson. They both come from even subdivisions of the circle. So they are, again, fairly common angles, and here we can actually use the side lengths of this triangle to find the trigonometric functions for each of those two angles. We'll start here with 60 degrees. So like before, we will do the sine first. Now, 60 degrees was 180, the half of the circle, split into 3 pieces. So for radians, that would be pi split into 3 pieces. Pi over 3 radians. Sine then is opposite. We're talking about the 60-degree angle, so the opposite is root 3 over root 3, and hypotenuse is 2. So the sine of 60 degrees, or the sine of pi over 3 radians, is square root of 3 over 2. Now, we're not as fortunate as we were in the 45, 45, 90 triangle to get where the sine and the cosine are exactly the same, because here the legs of the triangle are different lengths. Okay, so no big deal. We actually have to do a little bit more work on this one. The cosine of 60 degrees, or the cosine of pi over 3 radians, would be adjacent over hypotenuse. Oh, fortunately we got a nice friendly value there. Unfortunately, that's about where it's going to end. Next up is tangent of 60 degrees, or tangent of pi over 3 radians. Tangent is opposite over adjacent. Square root of 3 over 1, or just square root of 3. The reciprocal functions are, again, easy enough to come up with. Of course, these two, sine and tangent, have a square root of 3 in the numerator, so when we reciprocate them, we will have to rationalize those denominators. So we will again start with cosecant of 60 degrees, or cosecant of pi over 3 radians, and that would be the reciprocal of this. 2 over the square root of 3. Well, like before, if we do this just briefly down here, to rationalize the denominator, fortunately it's a simple enough radical down there. All we have to do is multiply it by itself, and then multiply by the square root of 3 in the top as well. This gives us 2 times the square root of 3 in the numerator. Not much we can do with that. But in the denominator, we get the square root of 3 squared, which is 3. So 2 times the square root of 3 over 3. Next up is the secant of 60 degrees, or the secant of pi over 3 radians, which would be the reciprocal of cosine of 60 degrees. Well, that one's nice and easy to flip over. 2 over 1 is just 2. And lastly, cotangent of 60 degrees, or cotangent of pi over 3 radians. 1 over the square root of 3. Well, actually, that's very similar to what we had for cosecant. The only difference between them is what value we started with in the numerator. Instead of a 2, it's a 1. So instead of a 2, it would be a 1, which I guess we don't really need to write, do we? So, same denominator, same rationalization. The only thing that changed is instead of a 2, it's a 1. And those are the 6 trigonometric functions for 60 degrees. Now, we're going to write them out, but for 30 degrees is the complement to 60. So all that should happen is the cofunctions should swap their values. Let's test it out. Now, we kind of get used to thinking of opposite as being over here and adjacent as being down here, because we tend to draw our angles in standard position. And if you notice, I've been very careful throughout the PowerPoint and through everything we've done here to keep the angle that we're focused on in standard position, with one side flat along the bottom and the other side extending upwards, so that we are looking at something that, if we were to put it on the coordinate plane, would be in the first quadrant. I've been very careful to do that because that's how we're supposed to draw angles, so it kind of keeps us looking in the same places for the same things. So what I'm going to do is I'm going to redraw this triangle. We don't need to derive it from the equilateral. We got everything we need. We just need to reposition it. So we just have to remember that the 1 is opposite the 30 degrees. So when we draw this out, and forgive me, I'm not an artist, so it might not be perfectly to scale, but the 30 degrees down here now, the hypotenuse is still 2, and the 1 is opposite the 30 degrees, which makes this side the square root of 3. So I'm going to leave the trig functions of 60 degrees up here because I want them for comparison. But what we want to do here is look at the trig functions for 30 degrees. So we have sine of 30 degrees, which is, in radians, well, 30 degrees was half of 60 degrees. 60 degrees came from dividing the 180 into 3 equal size pieces. We now need it split into 6 equal size pieces. So sine of pi over 6 radians. So sine is again opposite over hypotenuse. Note that that's the value that we had up here for cosine. So we have cofunctions of complementary angles are equal. Cosine of 30 degrees, or cosine of pi over 6 radians, adjacent over hypotenuse. With, again, no need to rationalize because the denominator is a rational number. And once again, we see that the cofunctions of the complementary angles are equal. Tangent of 30 degrees, or tangent of pi over 6 radians. Tangent is opposite over adjacent. Now, that requires some rationalization, yes, but I'm going to save us a little bit of time here and say, hey, look at that. the co-functions of complementary angles are equal, which means this should rationalize the same as this one, as root 3 over 3. The reciprocal functions follow easily. The cosecant of 30 degrees, or the cosecant of pi over 6 radians. Well, instead of looking at the triangle, instead of looking at the sign up here, I'm going to go right to the cofunction relationship. Secant is the cofunction to cosecant of the complementary angle is equal. If we use that relationship, it can save us a bunch of time here. The secant of 30 degrees then, or the secant of pi over 6 radians, should be equal to the cosecant of 60 degrees. 2 over root 3, which rationalizes. It's 2 root 3 over 3. And lastly, the cotangent of 30 degrees, or the cotangent of pi over 6 radians. Cotangent is the cofunction to tangent. The tangent of the complementary angle is root 3, so this should be root 3 as well. Understanding that relationship is very helpful because it saves you from having to have all of this stuff memorized. Understanding the reciprocal relationship means you don't have to constantly recalculate all of these. If you can do the sine, the cosine, and the tangent for an angle, you can get the reciprocals and you can get the cofunctions of the complementary angle. And there it is. It's not that difficult of a thing to work with if you know the relationships. And that's really the best way to get through trigonometry, is to understand the relationships between things so that you don't have to be sitting there memorizing a whole bunch of formulas, because if you go far enough with trigonometry, you realize there is an awful lot of formulas out there. But if you know the relationships, it saves you a boatload of memorization. So again, if we know these, getting these is not that big of a deal. And vice versa. And of course, if you know the sine or the cosine or the tangent of any angle, you know the cosecant or secant or cotangent of that same angle. Now, there are a lot of other angles out there, and eventually we will learn how to work with them. But for now, we've got 3 very, very common angles that show up, and we've got the trigonometric values, or the values of the trigonometric functions for those angles. 30 degrees, 60 degrees, and 45 degrees, or in radians, pi over 6 radians, pi over 3 radians, and for 45 degrees, pi over 4 radians.